So, oh, we're doing this thing again, aren't we? Alright, so we're about to do some questions. And so, just to get you guys, working and how to do something like this, I'm going to switch over to this. So right here, this is a challenging question right here in front of us. So we're going to do this one right here. And I'm going to ask for your assistance. So what you guys are going to do is, I'm going to call someone in chat and I'm going to tell you where you think, I'm going to ask where you think we should put the vector here. Now, I'm going to tell you, for a question like this, it looks simple enough, but it is not. Because you guys are probably wondering, what is this line, right? That is rho. That is the radius that's the radius of this center right here. And also, one more thing we most note about this question is that this changes, right? That radius, like location right here, it moves very clearly, right? If this thing rolls this way, so let's say we pull this scythe-looking thing down, this radius part, or the center of this circle, is now like way down here, right? So we have to include something like that in our question, in our vector loop. And the reason is because in like rolling contacts or roll slips, you have to include the center of the rotation always. Basically in every question. And the reason is because in future chapters, there's something called the rolling contact equation, where you have to basically part of your like let's say you had two equations and two unknowns, or three unknowns and two equations. Your third equation is a rolling contact equation, which involves the center of this radius versus another center of the rolling contact. So basically, in your vector loop, make a habit of including the center of this. With that in mind, let's go ahead and start. So we are going to start from here, because that is the input link, and so we are going to start there. So let me call on, let's go Sean. Sean, where do you think the first of these should go? The first line should go. You probably got the easiest one. Left. Is that left enough? So be a little bit more descriptive with it, or else you're gonna, through link 2, so you're saying it goes up like this, right? Stop me when I'm there, something like that. That is correct. So we're good there. I'm gonna call this R2, and you guys should do the same. So this right here is our first one. And remember, guys, this follows the rules. The rules is, for a revolute joint such as this, you go all the way to the end of the revolute joint, right? So this is good. Right where we're at is good. Now this is the confusing part. This is the trickiest step in this whole vector loop. So let's go with Jackson. Why not? Since I've been talking to you a little bit today. Where do you think we should go from here? Now, like I said, be careful. I mentioned something just a bit ago, that we have to include something in this vector loop. So, and think about this right here. This point, so this right here is a roll slip, I do believe. Which means that this basically these are in contact with each other, and it's like rolling and slipping or sliding on this point. So it's important to know where this center is as this happens, right? Anytime during this mechanism's rotation, we need to know where that center is. So with that in mind, where do we go from here? And if he's not, oh, he is there. Straight from R2 to the center of the circle. I like that a lot. So let's say something like that. And real quick, whenever you go to a center of a circle, it is customary, or generally in this class, is you label it something like RC. R sub center, I think is what, I guess, what they would call it, but R sub C. I like that a lot. Now, let's go to the next one. Junlin, are you here? And if he's not here, we're going to go to Rosendo. All right, he is here. So where do you think the next vector should go? So we have R2. We have this link right here. We have going to the center. Jackson and Sean have taken care of that for us. So where should we go from here? This is the point we're at. Where should we go? This one's fairly straightforward as well. So don't overthink it. And that's what a lot of people tend to do while making these. They tend to overthink it. So where do we go from there? No idea. Okay. So I appreciate your honesty. So right here we have link 1, link 2 is this, and link 3 is that. So right now, what we have accomplished in our vector loop is we know the position of R2, right, which is link 2, right? We got that. As this thing moves, as R2 moves, we know where the center of this curvature is, right? We've gotten that covered as well. There's one thing, so there's something we haven't covered, right? So what haven't we covered in this, right? We've covered this, we've covered the center. What haven't we covered? There's another joint that we haven't even talked about, or we haven't even been near yet, right? So where is it? Where is the next joint that we haven't talked about? I'll give you a hint. It is a J1 joint. Everyone's forgotten J1 already. In record time. The other ground. That is correct. So you're saying like something like this? So right here. And I will call that R3. So I like that a lot. I think that is a very good vector. I'm happy for it. So far in this vector loop, we have covered the length of this link, right? The center as this thing moves all the way around, right? And the distance from this center back to the ground over here. All right? Now we have to make this a loop though, right? So does anyone want to take a stab at where we go from here? Where is the last one? One sec, I gotta get rid of it. I'm taking this off. It's a loop, remember? So how do we make this into a loop? Because right now it is an open-ended vector, right? We've just went here to here to here. We need somewhere to go now. There was something I said yesterday, and I said something to the effect of a lot of times once you get to the ends. Remember when I said something about R1 is used and reserved for labeling ground links, right? I said a lot of times when you get to the end of the vector chain, the ground, R1 in this case, is just connecting the grounds back together. So with that in mind, Muhammad is going to tell us the answer here. I hope. Nope. He just stopped. He's like, no, I'm not feeling it. No answer today. So, where is this next one located? With that in mind, like I said, it has to be a closed chain. So where do we go from here? Down from R3, then to R2. So you're saying like here, and then what, all the way back to here? Is that like where you were? Sorry, that was the world's worst drawing. So you're saying something like this, right? Oh man, this is gonna always be bad, isn't it? This line is straight. Just for your information, it is straight. Okay. So you are saying, let's call this one R4, I guess, and let's call this one R1. So what you are suggesting is that we do it like this. And so I don't see any issues with this, actually. None whatsoever. But the actual, so this one right here, I actually think you could do it like this and there'd be nothing wrong with it. But the solution that they're going to show, so Jackson, I do agree with you, you are right. But the solution, they just do this. Straight back to there. And call that R1. But I agree, you could do it like yours as well. And the reason is because you have added nothing, essentially, added no real unknowns, because if you go down to here and straight up, that's once again straight, guys. Just, I have a problem with straight lines. I didn't spring for the line tool. So, we call this R1. So, if you did it this way, R4 is not changing, right? Would you agree with that? R4 is not changing. It's just some distance downward, right? So R4 is not changing. Neither is theta 4, right? Theta 4 is also not changing because this angle is going to be the same no matter what. Because essentially you're just connecting this point to this point at all times. This is not changing as well. And if you, now real quick, what would we need to do though to eliminate another unknown? Because R1 or theta 1 right here, how could we get that to be 0? Anyone like to take a shot at that? Remember, guys, make the coordinate plane work for you. And so, and if you did that, theta 1 would be 0, R1 is a constant, R4 is a constant, and this distance to here is theta 4. Theta 4 is also not changing. So, now, however, though, it would still make things a little, it wouldn't be as nice in another sense, is because if you you added another vector, and therefore you've added another cosine and sine and all that, so it's not nice in that sense, but you can do it like this. I am pretty sure, actually I'm 100% sure you can do it like this. So that is not bad, but once again, I would not, so don't get into a habit of just drawing down like this. So don't like go from the bottom here and then always back to the top. I would suggest sometimes just taking the easiest path, which is right, well, if I could actually draw this, take the easiest path straight across. So the only time I would suggest you doing what you did, I would suggest doing it on sliders that are on different levels, right? Something like that. But yeah, I would draw straight across here. I think that might. So I think you can both do it. I think you can do it both ways, and we'll actually find out here in just a second. So real quick, I'm going to zoom out and I'm going to redraw this because I draw on my screen. So let me zoom it out real quick. So I'm going to go to the answer. So right here, is the vector loop that was drawn. And so, as you can see, what he did was, whoever made this, which I'm pretty sure I know who, what he did was he went to here like Sean suggested, straight down to the center here, over to there, and back across, right? And so, that is his vector loop. So he did R2 minus RC minus R3 plus R1 equals 0. So that is basically it. And then, as I said earlier, he set the coordinate plane right here. So therefore, he could eliminate R1 as a variable, right? Where R1's angle is, or theta 1 is equal to 0, right? So real quick, let's go ahead and do the knowns and unknowns of this. So let's do unknowns here. This is where you guys are going to start making your money here. So what are the unknowns for, actually, well, let's start out with knowns. Knowns will help us a lot here. So let's do knowns. I think I like to do knowns first because it eliminates things that you need to keep track of. So let's do knowns. What on here is a known quantity at all times? R2 is definitely known. I agree with you. So let's put R2 here. And something else is also known about 2. It is theta 2. And the reason why it's theta 2 is because it is the input link, if you guys remember that term. It is the input. We know what it is. Is that, shit. Does that make sense? So what else do we know about this one at all times? So you say R3 and RC. So R3 is this right here. And we have Muhammad coming in with R1. So those are all correct. I agree with you. So RC, so essentially this right here is just on the circle, right? So this is how I would explain this. So essentially if you took this and slid it down, right? So let's say we have this moving downward. That means that this is now moving, let's say it's now here, right? So R2 is now here. So if R2 is now here, the center of this whole curvature has moved equally, right? Because it's a connected piece. So it's moved equally, which means that RC will always stay the same. It's just, essentially it's a radius of a circle. So RC is correct. And we then had R1, which is also correct because it is connecting two grounds, right? Two grounds connected, they're never moving, therefore R1 is correct. Anything else? RC, R3. Do you think R3? Are you sure, Jackson? So Junlin, the reason why RC is known is because basically it's just it's basically a center of it's just a radius of a circle essentially. We have, as this thing moves. So let's say this moved down, right? So it's going to be hard for me to draw, but essentially as this part moves down, so let's say we move this down, right? This center is moving along with it too, because remember that basically this C3, this center point, is the center of this thing's curvature. So as it stands right now, where it's located, because it is the center here. So if we draw this out, the center of that circle is right here now. But because this thing can move, so let's say, so how would it look where it is now? This is another possible position, right? Right? Instead of it being so high up, it could be almost horizontal. That means the center of the circle is now down here, right? You see how the center of the circle moved? And since it's like that, that means that this point is now further in on it, like over here somewhere, like that paddle, and the distance has remained the same because essentially they're at the same point. They move equally to each other. Does that make sense? So RC is always going to be the same distance every time. So one sec, I need to erase some of this stuff because I confused myself here. So if this C3 is here, you have RC. And then if we put this all the way down, so let's say I have to draw this out because it's hard telling. Yeah, I think you're right. So I think you're right. I think R3 is also known. I think you're right. Because essentially it's always on this row from the center point. And since this is the center point of this whole circle, right? Like if you continued this circle around, it's just a radius from it. I think you're right. I confused myself there. I thought you were wrong, but you are correct. So R3 is another one that is known. Now let's do some unknowns here. So we basically covered all the vectors, right? Every vector here is basically known, right? What are we missing then? We're basically just missing thetas, right? So that means, let me ask you guys this question. So theta 2 right here, obviously this is theta 2. Let's do this one right here. You would say that I would say this is theta C. So real quick, since we're on theta C, will theta C change? So as this center moves, right, as this thing moves around, will this angle always be this exact angle? This is where you have to use your mind a little bit. And like I said, drawing these things out is extremely helpful. When I put things in 3D, like in the SolidWorks or the Autodesk, it makes things so much more clear. Will this angle stay the exact same as this thing moves? The answer is no. It will definitely not. Because this thing is going to move further inward into here as this thing comes around it, and then let's put it this way. If I drew this thing out again, right? Like I said, this right here, I have it at a high point. This is if you turn it like 45 more degrees clockwise to get it all the way down. This paddle thing is going to be under here, right? Something like that. Right? So something like that. The center of this circle is going to be like, I don't know, somewhere over here. So essentially, this is now a more harsh, it's a more angled. It's actually bigger than it was before. So that's my point, is that one is definitely going to change as this thing moves around. So theta C definitely changing. What about R3, or theta 3? Sorry, theta 3. Theta 3. So as this thing, maneuvers around, will theta 3, this straight line, always be a straight line? Jackson, since you said R3 is right, or R3 is not changing, you tell me if theta 3 is always going to be a straight line there. It will. You say it will be a straight line. Why? I gotta get rid of this. One sec. Let me draw out the coordinate plane again. So R3, I would say, is something like that, or theta 3. So will this line, so remember, this center is moving though, Jackson. Remember, as this thing moves, this center point, this X mark, is moving down here. Or it can move up here, right? So will it always be at whatever theta 3 is right now, which it looks like 110 or something, or 100 degrees? Will it always be 100 degrees? Let's say the center point moved down here. And I want everyone else to think about it as well. Because like I said, if R2 is a known length, wouldn't the center stay the same? So you're saying, no. So the center is not taken, it's not taken about this. We're talking about, so this right here, this row is a radius to this center point right here. And if this thing, I really wish I had I think there's a blank copy here. I'll use the blank copy of this. Probably be a little easier. So, okay, so basically how this thing is moving is that as we turn this, right? So if let's say I turned it this way, right? If I turned it this way, this contact is always staying contacted, which means that this link right here, where we are currently at, will now be over here somewhere. And since it is now over there somewhere, that means this part right here is now further over here. It's actually moved this way. Which means that this center point, which I guess we'll put right here, is where it currently is. But if this center point, if this is now further this way, dragged across it, that means that the radius, so R3 will get shorter. Which one is R3 again? Wait, was I right in the first place? Uh-oh. So you're saying this one right here. So R3, let me see. So as this thing, no, I don't think it will. Because if you moved this down here, so remember, this, essentially this R3 distance is the distance from this ground to the center of this circle. So if you drew this out right here, and you created, essentially it's this distance right here. It is that distance. And so if you created a circle with just that in mind, which I know that's going to be really difficult, basically something like this. As that thing moves, so as this center point moves along this, R3, well, if I drew it better, maybe it does look like it'll get shorter. Maybe I was right in the original part. Uh-oh. Did I confuse myself again? Well, it's hard to tell because I can't draw it right. That's the problem, is that I can't draw it. But my first instinct was that it did change. I don't think it does, though. I don't think now. I don't think it does. I don't think it does because, like I said, if you. So what I should do is I should draw this in Autodesk, and it will make it more clear. And I think I will. But essentially, as this point moves along its track, remember it can only move as it pertains to this. So essentially, its distance doesn't link 2 move in as link 3 moves out. Yes, it does. Correct. So link 2 will go this way, link 3 will go this way. But the thing is that this distance, this center point, is taken always with respect to essentially this right here. And so it is essentially a circle. Once again, if you draw this around, which I can't because I don't have a circle tool, essentially that center point is always going to exist on a radius of the circle. Because this is basically right. It's the center point of this. So this is the center. This R3 is the radius. But this right here, this C3 can only exist on a radius of this circle. So I don't think R3 changes. I don't think R3 changes. But theta 3, on the other hand, does. And what I'm going to do for you is I'm going to draw this in Inventor. Because this is a confusing question, and I remember last semester we had problems with this one. But I will draw this in Inventor, and next class I will show you what it is. And I believe that the 3 unknowns are theta 3, theta c, and theta 2 is unknown, but we know it because it's an input. So they're right here. So the unknowns were theta 3 and theta c. And like I said, it gets some taken used, or you have to get used to how these things move, and not always is it very obvious how they move. Sometimes it's really hard to understand. But this one right here, I will draw this, and I think it'll make much more sense when I do so. But this is the correct vector loop. The unknowns, so are you lost on the unknowns at all? Like, I'm talking about the theta 3 and theta c. I feel like you're good on that because it's pretty obvious that as this center point moves, so like let's say since the x-axis is here, this is theta c or theta 3. If the center point moves down here and R3 now has to be here, it's now a bigger angle, right? I don't think we're lost on that. Would you say? I think that one is the angles are the easiest ones to figure out. It's the R's, I think, that are always difficult. But remember, so this vector loop, this is another thing that I probably should have made more clear, is that these vector loops are changing every step of the way. But the thing is, obviously, we can't draw them like a flip book and show them as they're changing the whole way through. I mean, you can on Autodesk, but the point is that since we're looking at a stationary picture, this is what the vector loop looks like now. But if we turn this thing even 20 degrees, it could look like this, you know? Here's R3, you know, this is back to R1, this is out there too, and then this right here is, this right here is, well, I didn't connect those very well, but you see the point, right, is that it could look like this, which is just a distorted version of the first one, right? Because R2 here, C here, 3, and 1. So you see the point is that as you move this thing, it changes. The vector loop changes, but you have to know what parts of it are staying the same. And this R2 is obviously staying the same because it is just it's a link. It is just a normal length of maybe 10 feet or 3 feet or whatever it is. It's not changing because we have grounded here and it's up to a point on this link. It is not changing, right? And so you have to know that as these things move around, what is changing and what isn't. And I'm going to draw this on Autodesk. I'm going to take attendance here in a second, so you guys will be good to go. Tomorrow, we are going to I'm going to try and do multiple examples of this. I'm going to show this at the very beginning. I'm going to show what this looks like on Autodesk and how it, if we move it. I'm going to draw lines, and the lines will be how things look one hand and how they look another way. And I think you guys will probably get a better sense of how these things work after that. And then I'm going to do another couple questions like this, specifically like this, not this confusing, but of this difficulty, and then